Hello guys, Akshay here. Today we'll be discussing the thermal axis of fins, which are heat transfer elements. Okay, using ANSYS APDL. So it will be a different procedure. Let's go into the basics of a fin at the first thing, and we'll go into the ANSYS part. Okay.
So a fin is nothing but a conducting element that is attached to the main component from which heat is supposed to be removed. Uh, it serves the function of removing heat from the component it is attached to as said. So the longer the length of the fin, the more effective the heat transfer will be. And there will be two main classifications of fins based on their ends. So with ends that are not insulated and ends that are insulated. So those two will have different parameters. And if you can see, there are also different types of fins based on their shapes. They can be square or rectangle or circular or triangular. As of now, triangular fins are proven to be more effective than any of these due to its effective heat conduction. And so we will go into the analysis now using ANSYS APDL. So I would essentially construct a small plate and a fin-like structure. Okay, so into the ANSYS video. So here I open ANSYS now. ANSYS is opened. So today, this time we'll be discussing about the thermal analysis of fins. Um, I have already discussed about the functionality of fins, and so I'll be directly going with the analysis. Uh, so I need to prefer a mode of analysis. It should be a thermal analysis. So I need to pre-process, for which I need to define an element type. I have to add an element type. It is going to be a solid. It can be either a quadrilateral 4-noded mesh or a triangular 6-node mesh. That is up to our own convenience. I give quadrilateral 4-noded mesh. And to note, you cannot perform a 3D fin analysis in APDL. You need workbench to perform a 3D analysis of fins. However, a 2D analysis is possible. So here I perform 2D analysis. So I don't have to give any thickness. Okay. So yeah. So I don't have to give any uh, material models. I need to define the material. So I go into material models. Material model one. I need the thermal conductivity of the material model one. As I said, isotropic is for metals and orthotropic is for composites. Anisotropic option is not listed here because anisotropic components usually are poor conductors of heat, so they are not going to be used for your consideration. So isotropic or orthotropic will do. It is isotropic here. So material model 1 is stainless steel, which will have a thermal conductivity of approximately 45. 45. Okay. Next comes the material 2, which can be aluminium. For aluminium, I can define it to be like around 205, 205 watt per meter Kelvin. So I have defined the material. I need to create key points. For that, I need to have a work plane display because rather than creating an active coordinate system, creating it on a working plane will be easier. So I need to change the settings of the work plane. I need to have a snap. So okay, Cartesian coordinates, yes, and I need to display the working plane. So yes, I zoom out for my convenience. Now I create the key points on a working plane. So yeah, like this. It is your own random choice. Here, you can create it here, you can create it here, you can create it here or anywhere you want. That depends on your own convenience. Fins can also have variable length. That is totally up to you. Design of fin determines its efficiency. So everything is up to you. It can be a 3 fin or a 4 fin component. The more the number of fins, the more will be the efficiency. So also that is up to you. Okay, so I have created my required key points, I guess. I have to unpick one because I created one wrongly. Sorry. Okay, now I have to create one. Yes, I have done it. So, okay, I have created the necessary number of key points I need. And yes, now I have to join these with lines. So, before that, I can remove this work plane. And before going for something, I need to do one. Before going for creating the lines, I need to go for one thing. I must remove the uh, extra key point that was created accidentally. So I go to delete key points. I pick the third key point. Okay, and yes, it gets deleted. So now I go for a line, straight line. So one key points are joined like this. Like this, I join the key point. Okay. So again, I have to close like this. Okay. Yes, I have finished marking the lines. Now I have to merge the base material into one area and the fin material into another area. So what I do is I go into area option, arbitrary areas by lines. I pick the lines I have. These are the lines that I created. So I pick these lines. First I decide to define the fin area. So I do that. So I bound the fin by its area. Now I decide to merge the base part into one area. So here I also do that. However, yes, there was a mistake. So okay, I merge this into an area. Next, I have to mesh it. So I go for a fine mesh for more accuracy. So I close this option. Next, what I do is I choose mesh attributes, picked areas. I choose the fin. I choose the base part now. It is stainless steel. Now I have to choose the fin part. Sorry, I have to choose only the fin part, and I define it with the property of aluminium. Okay, it gets defined. Now I have to mesh these. Under areas, you choose free mesh. You pick the base part and have it meshed, and choose again. It may seem to be invisible, but once you pick near that, it will show a yellow color. Show some yellow color indicating it is visible again. So it gets visible. Yes. So it gets meshed now. Yeah, that's all. Meshing is over. Now you have to apply the load. Uh, it will be a convection load in the fin part. So you have to define the heat transfer coefficient H in terms of watt per meter square Kelvin. So convection on lines. I choose each line like this, 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 and like this, and like this. It gets done. So I need to define a film coefficient. It can be around 100 or so. Like this setup is assumed to be like placing it in the air, which can have a film coefficient of 100 watt per meter square Kelvin. So a temperature will be like ambient temperature. It can be at ambient temperature. It is also simply 100 degrees Celsius, but I write it in Kelvin, so it's 373. So this gets applied, and I need to see how much heat is generated over here. Heat generated on areas. So I choose this area. As I assume to be it to be 1.5 E6, E5 or E6, whatever. Assume a higher value and proceed for the solution. I just solve the current LS. Solution is done. I have to choose the general post processing. I need to take the contour plot. It is a nodal temperature solution that I need. So yes, it is proven the base part is heated the most while the fin part is heated the least. Okay, so the fin part is heated the least. At towards the end of the fins, you can see that heating is very minimum. However, at the base part, you can see the red color, which indicates the heating is maximum. So yeah, that is done. Thank you. Uh, Thanks for watching.